Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, in today's video, we're going to be looking at energy and chemical change. Okay, yes, it is a topic that is assessed both in grade 11 and 12. Okay, those doing grade 12 inherit this topic from grade 11. So, if you're doing grade 11, you have to watch this video i- in term 3. Okay, yes, if you are in term 3 currently, then this video is suitable for you. But if you are still doing term 1, term 2, just keep it for now. You'll do it in term 3. But if you're doing grade 12, you need this fundamental so that you can be able to take this information I'm going to give you to apply it also on the topic that is assessed on grade 12, which is rate of reaction. Okay, yes, so if you're doing grade 12 from June up to final, this is for you. Okay, now let's move. Now you'll first start by defining what is an exothermic reaction. So we say now exothermic reaction, it is what we say it is a reaction, a reaction that releases releases um, a reaction in which energy is released. Okay, that releases energy. Okay, or a reaction in which energy is released. Okay, more than it absorbs. Okay, yes. For an endothermic, we are saying it is vice versa, a reaction in which now is absorbed than it is released. Okay, let me write a proper definition. A reaction in which energy is released than it is absorbed. Okay, yes. So now this is a definition thereof. Now, an examiner might give you this and say to you, for an exothermic reaction, now what happens? The delta H is less than 0. Okay. So how did I manage to know this one? So I want you to check it like this. If it is like this, I want you to take it as a something maybe that does what? That releases. Can you see it releases? It is a mouth that releases energy. Okay. Can you see if it is looking like this? It releases energy. Okay. Yes. But on this side, it absorbs. Sorry. It absorbs. Sorry. Like this. Absorbs energy. Can you see? Now it absorbs energy. Energy is being absorbed then so that it can be released. Can you see that? Yes. So now we have a formula for a what? We have a formula for changing H. So we say changing H, which is enthalpy, changing enthalpy, or now changing uh, heat, maybe heat of a reaction. Okay. So we say changing H, it is now energy of the product subtract the energy of the reactant. Now, I want you to take note of something. We say for this one instance, changing H is less than 0, right? So if changing H is less than 0, we now expect this one to be less than this one. Why am I saying that? If this is 5 and this is 10, and when we subtract, if this is lower and this is higher, can you see now our change in enthalpy will get as a negative, and less than 0 means negative. Okay? Greater than 0 means positive now, in case you get confused. Okay, so can you see now 5 minus 10, it is negative 5. So now our change in enthalpy is less than 0. Now, therefore, it means now for this reaction now, the energy of the product should be less than the energy of the reactant. Okay, yes. But in this case, our change in enthalpy still uses the same formula. It is the energy of the product minus the energy of the reactant. But in this case, since well our change in enthalpy is greater than 0, this need to be higher than this one so that it gives us a positive number. Again, therefore now it means now for this one, energy of the product is greater than energy of the reactants. Okay, I want to believe you are following. If you understand this, you are in a position of throwing a graph there off now. Why am I saying that? Because now throwing a graph is you saying now, okay, I might have this. It is slanted a little bit. Okay. Yes. Let me copy that and come here and paste it in here. Okay, because I'm still gonna use it also on this side. Yes. So now I'm saying now this is energy of the reactants, this is energy of the product. Okay, let me say energy of the for now we are saying for exothermic reaction, which is this side, we are saying the product should be less. So it means this one should be energy of the let me move my graph a little bit to the side like that, like so. Okay, yes. So we are saying here it will be energy of the product since well they are less, right? Then this will be energy of the reactants. But in this case, let me okay. In this case, can you see now the energy of the product is higher? So it means this one is energy of the reactants. Then this is energy of the product. Okay. If you know this part, if you understand this part thoroughly, this one, you'll be in a position of now being able to draw a graph. Okay. So now every time our reaction starts from the reactant, so it starts from the reactant, right? Therefore, it goes to a point that I'll explain later on. Then it comes back to the product. It starts from the reactants. Sorry if I said product. It starts from the reactants to the product. But here, similarly, it also starts from the reactants, but it will end where to the products. But it will go to a point where I'll explain now. Therefore, it ends to the products like that. Okay, yes. So these are our two graphs. So this will be the course of reaction. This will be the energy. Okay. Now I want you to see something. There is an important a point. The highest point there it reaches. It is a point where that we call a sorry, not complicated, activated complex. Okay. So we call this point activated complex. Okay. Now activated complex. Now it is now defined as the unstable transition state, okay, between the unstable transition state between the reactants and the product, okay. So now it is an unstable transition state between the reactants and the products. Similarly here, this is what we call the activated complex also, okay. Yes, but now the most important part, it is now what we call activation energy, which is the minimum energy required for a reaction to occur. Okay, so you now say the active, but now what is that? Let me say now this is extended that. I might need to extend this also. So let me say now this is E1. Okay, E1. Let me name this E1. So now energy from this is the energy of the activated complex. Can you see? Yes. But now I want you to see something. From the energy of the activated complex here up to the energy of the let me redraw that from here up to here, which we call from any this line from energy of the activated complex or energy of the highest peak or the peak to the energy of the reactants. From here, from the energy of the peak to the energy of the reactants, we call that an activation energy. Okay, you can write it activation energy like this or like this is still fine. Okay, now what is an activation energy? It is a minimum energy needed for a chemical reaction to occur. Can you see now? From energy of the reactant up to the activated complex, which is now the unstable state. Now, this is the minimum energy we need. When we have this energy, E1, When we have that energy, it means now our reaction can start to occur and now produce. Okay, similarly here, from the activated complex up to the energy of the reactant, can you see it is what we call EA, the minimum energy required for what? For the chemical reaction to start or to occur. Okay, yes, this is what you call the, let me define that. Let me remove this. Yo, it's gonna remove. Yes, yes, I knew it. Ugh, how can I do that? Okay, let me. It's fine. I'll. Oof, don't wanna remove this, all of it. Okay, but it's fine. I wanna explain something. Okay, I'll redraw that graph. That graph. I'll try to redraw it using a ruler because yeah, I'll try to redraw that. Even though it won't be perfect, nice, it's fine. Okay. Uh, yes, perfecto. Good. Thank you. Now, I want to explain something. Okay. Now, we talked about what? Uh, activated complex. So now we explain activated complex as the what? The unstable transition state from the reactants, okay, to the products. This is what we refer to the activated complex. We also had a definition again that says now activation energy. Can you see from the word activation? It is an energy needed to activate something. Okay? It gives the activation of the reaction. So now we say this is the minimum energy required or needed required for a reaction, for a chemical reaction to occur or to start. You can say the minimum energy needed for a chemical reaction to start, okay? Or minimum energy needed to start a chemical reaction. However, the English that you English there, okay? Now I'm gonna, this topic, it is a very 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 nice and straightforward topic. Okay, I'm gonna move to what we call a catalyst. A catalyst. Okay, I'm gonna define a catalyst. You already know a catalyst from life science, right? So remember, in life science, we say it is a substance that speed up the reaction. Okay, in life sciences, we say it is a substance that speeds up the reaction. But now in physical science, specifically chemistry, we'll define it in a little bit different way. We'll say now it is, yes, it will be the same, but there is some few concepts that will add. Okay, so we say now a substance, we say it, a catalyst, it is a substance that speeds up or increase the reaction rate remember we are talking about the reactions here. A substance that increases the reaction rate or the rate of reaction by doing what? By lowering the activation energy without it undergoing any permanent change, right? So I wanted to show you the effect of a catalyst on this graph. So when we add a catalyst thereof, what will happen is that now our graph will look something like so. Okay. Now let's come back from the definition. It is a substance that increases the reaction rate by lowering the activation energy. So it means, now remember, the activation energy, it is the energy from the what? From the activated complex to the energy of the reactant. So this one. So if you want to decrease this, so do you agree with me that this peak should be a little bit here, okay, at a lower position, whether here or here, as long as it is lower, right? But now I want you to see something. Can you see now our reaction in this case? It starts from here and it goes there, then it comes there. So if you want to speed up the reaction, we should start here and maybe cut it here and come back here. Can you see now we took a shorter route, okay? So now our reaction became faster, okay? So yes, this is what a catalyst do. But when you are asked to draw how a catalyst affects this, you'll say now it starts from the reactant. Instead of going back there, it now takes a shorter route like that. Then it will end there. Okay, yes, it will start at the same reaction energy of the reactant and end at the same energy of the products. But now what will differ is that the energy of the activated complex will be lowered. Okay, meaning now the energy of a activate sorry not the energy of the activated complex, the energy of the activation energy will be lowered. Can you see now the energy of the activated complex will start from the peak up to the energy of the reactants? Can you see now it is now lowered? This is our new ea. This is our new ea. Can you see that? Similarly here, the effect of a catalyst, it will start from the reactants. It will go there and take a shorter route and now end where? At the reactant. So now can you see now our activation energy? Activation energy, it is now lowered. Okay. Okay. So now the effect of a catalyst, it does what? It increases the reaction rate. It increases the reaction rate by doing what? By lowering the activation energy. It only affects the activation energy. It does not affect the energy of the product. It does not affect the energy of the reactant. Please take note of that. Okay. Yes. Now quickly, I want to talk about something forward as well as the reverse reaction. Now what we are given here, let me do this. If I'm given something like a plus b in a reversible reaction, then it gives me AB. Then let's say they say now to me changing H is less than 0. Now, this energy that I'm giving here, it is the energy of the forward reaction. We are referring to the forward reaction. Now, why am I saying forward reaction? Because this is a reversible reaction. There is a forward reaction, there is a reverse reaction. Hence, we are saying it is a what? A reversible reaction. It goes like that, not like this. Okay, yes. But yes, now this energy that the examiner gives you the energy of the forward reaction. So it means now the forward reaction, it is now changing H, it is less than 0. It means the forward reaction, it is exothermic. Meaning now what does this tells us? This tells us that the reverse reaction will be endothermic, endothermic. Okay. Now this is what I want to explain. And if it is exothermic, remember, it is like this. It does what? It releases energy. So it means I can say plus energy in here. This will be very important, especially when we deal with chemical equilibrium. Okay. So, okay, the examiner can give you change in H is less than 0, or can give you an exact value and say maybe change in H, it is equal to negative 212.5 kilojoules. Like that. Okay. This is the same. Changing H is less than 0. Remember, I said less than 0 means negative. Now, how do I draw a graph like this? It will be a graph like that, maybe. Okay. So now, let's say it is less than 0. So it means the energy of the products will be lower. So maybe let's say something like that. Okay. So let's say this is 200. So this is energy. Okay. Potential energy in kilojoule. Yeah, let's say kilojoule for now. This is the cost of reaction. Okay. Let's say now this energy of the reactants here, it is something like maybe 80. Then this, let's say it is something like approximately like 30. I don't know. I'm just guessing. Okay, let me do it 50. Okay. Now you agree with me, this is A plus B, right? Forming what? AB plus energy, of course. Okay. Now let's try to remember them. Remember, this is what we call what? This is what we call our activation energy. Okay. Energy from the uh, activated complex to the energy of the reactant. So, oh, another thing that I forgot to mention here. Sorry, we have what we call change in age. Remember, change in age. I said what it is there. The difference between what? Sorry about that. The difference between the product and the reactant. So now, if I'm having the difference there, it will be something like this. This is what we call our what? Changing age. But now, can you see in this case, remember the formula says changing age, it is now energy of the product minus energy of the reactants. But can you see in this case, it is energy of the reactants minus energy of the product. So it means it's going to be like this. Can you see it is negative energy of the reactants minus minus what? Negative energy of the, or plus. Okay, let me do this. In this case, we have energy of the reactants subtracting the energy of the product, but we want it to be energy of the product minus energy of the reactant, so it is negative. I'm just rearranging negative ep plus negative er. If I want to make this one become positive, I have to take the negative factor, which is energy of the product, then this will be minus energy of the reactant. This is our formula, so it means now it is negative. Can you see now our change in h? It is negative in this case there of yes. Okay. So now this is what we call our change in age. It will always be an energy between our product to our reactants, like that. Okay. Yes. Sorry about that. Similarly here, I will have something like uh, from the reactants to my product thereof. That is what I call what? Delta H. Okay. Yes. Okay. Now this is for the forward reaction, okay? But if the forward reaction goes like this, from here to there, how am I expecting my reverse to go? And remember, these are my reactants, okay? These are my reactants. These are my product. So now this is for the forward reaction. But now for the reverse reaction, this will become now the 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 reactants. This will become for the reverse reaction. Let me do this. For the reverse reaction, this will be my reactant. Then go there, go there. This will be my product. So what does this tell me? This tell me that for the reverse reaction, I will have different things. What do I mean by saying different things? Meaning now, if these are now my reactants for the reverse reaction, and can you see now the reverse reaction, it is endothermic. Why? Because now can you see my reactants are low, my products are high. Yes, this is what I said there. Oh, okay, I removed it. Okay, but now if the forward reaction, this tells you about the forward reaction, which is change in H, it is less than zero. Therefore, it means now the reverse reaction will have a change in H that is greater than zero. Can we see that now the reverse reaction, it is endothermic? Okay, so now it means now this will become now from the activated complex to the reactant. Remember, you're talking about the reverse. This will be the activation energy for the what? For the reverse. Okay, I'll just indicate that by, yeah, by the reverse, like that. Okay, then now another thing that I might talk about, it is now the change in age. Can you see now the change in age is the same? The change in age is the same because these are my products, these are my reactants, these are my new products, these are my new reactants for the reverse. Okay, but now what will differ is that this one, the change in age, the change in age in blue, the change in H in blue, it is less than zero because it is an exothermic. But the change in H in an orange or whatever color it is greater than zero. Meaning, if you were to calculate here, I want you to see something. If you were to calculate here, the product is how much? It is 8. It's gonna be 80 It's gonna be 80 minus 50. These are my products for the reverse. Okay. For the reverse, this is 80 minus 50, which is how much? 30 kilojoules. But for the reverse, I want you to check something. For the reverse now, can you see now my change in H? What are my products? Are my products for the reverse? Okay, sorry, for the forward. For the forward, these are my reactants, these are my products. So 50 is my product, 8 is my reactant. So it means it's gonna be energy of the product minus energy of the reactant, which is 50 minus 8, which is how much? Negative 30 kilojoules. But can you see the magnitude is the same? The magnitude, which is 30, is the same, but what differs is the negative sign. Okay, yes. This is what we mean by the reverse reaction. Okay, so similarly, if a catalyst were to be added there, if a catalyst was to be added like that, a catalyst, therefore this will decrease the activation energy of both the forward as well as the reverse. Can you see for the forward will be something from for the forward, let me use a highlighter. For the forward, will start from here to there. Okay, for the forward. But for the reverse, it will start there up to there. But can you see now, compared to this, it is lowered. Okay. So that's all from me about changing H and energy. I mean exothermic as well as the endothermic reactions. So what I might do from now on, I will do two questions maybe based on these, so that we have a better understanding of how we apply this. Okay. So thank you very much, folks. I hope you will follow me moving on forward to dealing with these questions. So thank you.